Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Dear students, today we take up the binary tree representation. We have seen the binary tree and its types and all. Now we have two kinds of presentation, either the array representation or the linked list representation. So for example, I take up the tree like this. Let me call it as an A, this is a B, then C. Say for example, this link is missing, okay? This is not there. Then I got the D here. Say for example, this is also missing and this is also missing. Then I have the D, where I got a couple of kids, okay? This is the E and F. Now I want to represent this in an array. So how I got to represent it, what I do is I will put up an index here, 0, 1, 2, 3, 4, 5, 6, 7 and 8. So till now I got 8 nodes, so I'm gonna have an array of size 8, for example, starting from 0, 1, 2, 3, 4, 7 and 8. Okay, so what I do is I put up at the 0th location A, at 1 location I put up the B, at 2 C, at 3 I don't have anything, so I put up a null here, at 4 is D, then 5 and 6 again the null, and 7 is C, 8 is whatever it is, it was E, and it is F. So you could see here we have the indices, and the array index matches the tree index. So and if something is missing, so we deem it as a complete tree, okay? And if something is missing, we put up what? We put up a null there, simple as it is. Now this has its advantages as well as disadvantages, because it's simple to represent, so that's a kind of advantage. But disadvantages is we can have a sparse tree. Say for example, we may have a binary tree like this, A, B, C, D, E, and it may be so on. So what is happening here? This guy is missing, okay, and then from this is missing, these two guys are missing, and here this is missing, these two guys are missing, and I'm on this level now. Now from this level this is missing, or from this level these guys are missing, and so on. So if I want to represent it, I have to take a whole lot, okay, and I have only 1, 2, 3, 4, 5 here in the array, and rest of the places I have to put the nulls. So from the, if I got a left scaled or right scaled, or if the nodes are missing, so array representation is really wastage of storage space. So but array representation is good if we have sort of a complete binary tree. So in that case, binary tree representation array will be very simple. But in case of which is not complete binary tree, which has a lot of missing nodes, it wastes a lot of space. Okay, let me take another example here. If you see this example, okay, now here we got the 50, 25, 75, and 3 is missing, 7, 8 is missing. So at 3, 7 and 8 we got nulls. Okay, if you could see here, 3, 7 and 8 we got nulls, then 12, 13, they are all nulls. Okay, now by this way we can, this structure we can say who is the child, who is the father, who is the left child, who is the right child of a particular node. Say for example we take up the node 6 as an example, this node, that is 84. So who is the father or parent of node 6? So we can get it by having a formula, simple formula, that we got a floor of n minus 1 slash 2. So what is that? N is here 6, that is 6 minus 1 slash 2, that is going to be 5 slash 2, that is going to be 2.5, and if you take a floor, that is the lowest one, that is 2. So we are saying technically the 2 is the father of 6. So who is 275? So I'm saying 75 2 is the father of 6. Is it? So same way I can use this formula to see who is the father of any node. Then what about the left child? We can have a left child, we can have the right child as well. For left child, we got a formula 2n plus 1. Okay, say for example we got the 75 that is at 2, who is the left child of the 75, that is 62, which is at location 5. How we get it? Because here we are talking of n is 2 here. Okay, so 2 cross 2 plus 1, because n is 2, so 2 cross 2 is 4 plus 1 is 5. So we are saying for 2, that is 75, the left child is at location 5. So this is the left child. Same way we can have the right child. Okay, so our child. So where is the all child? Our child will be simply 2n plus 2 location. So in this case, say for example for the 2, n is 2, 2 cross 2 plus 2, that is 6. So right child will be at 6 and left child will be at 5 for this 2. Same you can apply for other guys. Okay, now if this binary tree representation by array is better for the complete binary trees. What about the right scaled or left scaled guys? For example, this is one of the example I've taken from the internet. Okay, this is a right scaled tree. In this case it starts from the 1 index, so 0 is empty, so we should better take from the 0, this thing with what I've shown. Then you can see because left side is everything is empty, so those places will be null. Okay, so see how many I've got 1 2 3 4 nodes, and rest of these guys 11 places we got the nulls. So that's a problem here. Okay, so if you have an n node binary tree, you need at least length between n plus 1 or and 2 raised power n array size. So for example we got this guy, so it seems to be filled. So if you got 3 nodes, so you need at least n plus 1 spaces as per this guy. If you see here, we need to fill up these 3 nodes. Okay, so and now this is 1 2 3, so 1 is here, here and here, so we got 4 n plus 1 nodes, n plus 1 array length. But if we have say for example right scales guy, we have a 3, but it's the rest of the things is left scaled, if the rest of the guys are missing. Okay, so how many are missing? So we have 1 2 3 4 5 6 and 7. So these 4 are missing. So 4 plus 3 is 7 and first one is 8, so I need at least 8 spaces. So that means 2 to the power n if it is totally left scaled or right scaled. So I got 3 nodes only, I got these 3 nodes only, the rest of the guys are missing. So 2 to the power 3 is 8, so I need at least 8 nodes. That's what 2 raised power n stands for. So if you have an n node binary tree, an array whose length is between, we need an array whose length is between n plus 1 and 2 raised power n, right? So this is the kind of overhead, so wastage of space. So why we use wastage of space? If we have what is called a linked list, so we can use a linked list representation where we have the 3 things. We have a node, okay, and we have the data part, and we got the left child link, and we got a right child link. Okay, so if at all I have a left child, then I will put the address of this left child into the left child. Okay, and this also will be a node again, data left child right child. If I don't have a right child, if we don't have to create a node for that, so it's as per usage. Okay, so if we have the right child, its address, say for its address is 1 2 3 4 for example, that will be here 1 2 3 4. So it's a pointer which points to this node. The data is the data part, so these 2 guys will be just a pointers which points to the addresses where the nodes are. Okay, and we have a data here, again the left child and a right child, and so on. Okay, it will go so on. So if I have the left child, it will be there. So if I have a right child, it will have the address of that here, and so on. So linked list actually will be created whenever you have a node. You will create a node and put its address into the left child. If you have on the right, you put the address into the right child. You don't have any kind of wastage of space. Okay, so this is an example of linked representation here. So we had an A node, for example. It has a left child of B, and then it has also the left child of C. Okay, now C has a right child E, So that's why it's on blue is the right child and yellow is the left child, and this one is the data. Okay, and E has a left child of G and G has a right child of H. So this is how the structure is. So in a B we got a left child D and it has a left child F. So this is how easy we can make it without wastage of space. Okay, in array representation we had to waste a lot of array indices for those who are missed out. Otherwise we can't say who is the father, because if we don't follow that structure we can't say who is the father of whom, who is the left child, who is the right child. So that means we simply cannot present the tree in an array. Okay, that is kind of a problem there. But here in linked list representation we have a pointers which can tell us where is the left child and where is the right child. Okay, if for example its left child is missing, okay, we don't have to, because if there were a left child it would have been in this the pointer address of that would have been in this pointer. Okay, but it's not there, so it's not there. So that means we don't have to waste space. There is also one special pointer called root. This is a pointer which points to the root node. So we need to have some kind of pointer which always points to the root so that we can have a start. If for example we have traversed this tree, you have gone somewhere, so how to come back, because we know we have a root which is always pointing to the root node, so we can start from again with this root. Okay, so we can get back to the root node by this root. Now we need to implement it using some program, and we also see the traversals in a tree, how to traverse this tree, how to read the data from a particular tree. Okay, so next video will be on a traversal of a tree. Until then, ma salama.